good morning and good afternoon, everybody. Firstly, thanks to the Human Traces Group for the invitation to this talk. It's a pleasure to be participating. I'm going to present some studies about the evolution of the environmental state of artificial lakes in Central Argentina, as Natalie has introduced, in relation to water quality issues. It is worth mentioning that most of the results I will show were obtained by the Geolimnology Research Group in the Earth Science Research Center, CONICET Argentina, of which I am a member. Also, I will present contemporary studies on the state of artificial lakes that were my first steps before jumping to the reconstruction of the past of these systems. So, sorry. Okay. So it is well known, we are transiting the Anthropocene era, which is the result of human disruption to the Earth system. This figure shows the current status of the control variable for the planetary boundaries. We can see that some of them closely related to freshwater systems like biosphere integrity, climate change, and biogeochemical flows are well outside of the safe operating space in the high-risk zone, highlighted here in purple. On the other hand, the component representing freshwater change here, freshwater change is in the increasing risk zone, a lower risk zone marked in yellow. However, this risk level includes changes across the entire water cycle over land, accounting for river regulation and aquatic ecosystem integrity, hydrological regulation of terrestrial ecosystems, climate, and biogeochemical processes. In this context, artificial lakes are main actors in the Anthropocene era and fresh water change. Sorry, some effects of artificial lakes, we have noticed that artificial lakes are part of this human disruption characteristic of Anthropocene era. And although they provide a continuous water supply for different purposes, such as electricity generation, human consumption, irrigation, flood control, livestock feed, and recreation, it is well known that reservoirs are controversial because they are crucial and acute impacts on the social environment. These impacts are generally well known and include, among others, the modification of aquatic and terrestrial socio-ecosystems, changes in the morphology of river systems, and degradation of water quality, among others. About degradation of water quality, this is the result of many processes as alteration in nutrient and sediment discharges, and also water column stratification. These processes can cause different events as phosphorus, remobilization, anoxia events, and also an eutrophication. Changes in the morphology of rivers are related to alterations in sediment discharge, which can produce sediment trapping in reservoirs and also modification on the downstream habitat and also community. In this picture, we have an overview of the global spatial patterns of the number of reservoirs, with the major hotspots concurring with larger or industrialized countries. For example, United States, China, India, Europe, countries of Europe and Brazil. By the other hand, the numbers in a smaller, drier, or less developed countries are very low. For example, in South Africa and in part of South America. And what about artificial lakes in South America? Here are shown reservoirs taken from the dataset of georeference dams in South America. This dataset contains 1,010 entries and is being improved with data from other databases. As we have seen before, reservoirs are strongly concentrated in Brazil. And in Argentina, reservoirs are mainly located in semi-arid regions as central, western, and northern Argentina. However, the monitoring of water quality in South American artificial lakes started 20 or 25 years ago, while older limnological studies are very scarce or scattered. For this reason, paleolimnological studies are fundamental to assess the evolution of the environmental state of these systems. Regarding paleolimnological studies on South American artificial lakes, most of them were carried out in Brazil. For example, here we have in the Sao Paulo region many paleolimnological studies, and in this case I show in the Atibaina Reservoir. Also, in Brazil, there are some studies in Paraná State at southern Brazil here, and this is the case of Itaipu Reservoir, located on the border of Paraguay and Brazil. And however, in the other countries in South America, there are very few paleolimnological studies on artificial lakes. One of them is the study on the Salto Grande Reservoir, located on the border of Argentina and Uruguay. And in the rest of Argentina, only in the central region, in the area of the Pampean ranges here, there are some paleolimnological studies conducted on the San Roque Reservoir by our research group. Okay, despite the general scarcity of limnological and paleolimnological studies in central Argentina, especially in Pampean ranges, there are numerous reservoirs in this area, mainly used for water supply. Here we can see some of them along the Pampean ranges. Here we can see also as reference Laguna Mar Chiquita, that is one of the largest lakes in the world. The San Roque and Los Molinos Reservoir are supplying water to the main city of this region, that is Córdoba City, and other surrounding towns, representing the supply for 1.5 million people. Both reservoirs had been monitored for water quality from 1999 to present, but there are no continuous monitoring programs for the other artificial lakes in the region. Okay, our case study, San Roque Reservoir, holds the distinction of being the oldest in South America, having been constructed in 1988. However, a second dam was built to enlarge its capacity in 1944. The main purpose are water provision, flood control, electricity generation, and recreation. San Roque is a well-studied system, monitoring monthly from 1999 to today by the National Water Institute, and it is well established that its trophic state has been eutrophic since 2012. And here we have some of the main morphometric and limnological features of this reservoir. Okay, in terms of water quality, one of the main concerns in this reservoir and in general in all the reservoirs of this region is cyanobacterial blooms and also toxin production. The most frequent and abundant cyanobacteria genera detected in this reservoir is microcystis, microcystis and oligospermum that are here. Here we observe the record of blooms over several years, revealing the conditions that favor algae most significantly. For example, the maximum values of microcystis have been recorded in summer with the onset of water column stratification and total phosphorus concentrations higher than 30 micrograms per liter. Looking for a first association between the environmental state of the San Roque Reservoir and the land use in the catchment, it is observed that land use is characterized by urbanization that is marked in light brown here, especially in the areas close to the reservoir. Here in after refer to as the perilacustine area, and along the northern and southern roads. Looking for the urbanization of the whole San Roque Basin, it is observed that experience a pronounced increase of approximately 200% from 1980 to 2019. Currently, the northern area is in the catchment is the most urbanized, followed by the southern and western area. We can see it here. When considering the urban growth over the last 40 years, the western zone has notably undergone the greatest increase, and we can see here comparing the different maps. Okay, but not only the urbanization is the unique process that is affecting eutrophication process in the basin. We know that fires are main drivers causing eutrophication and soil erosion in the basin. They are an important factor causing organic matter, nutrients, and sediment loading to the lake systems by decreasing vegetation cover and water infiltration as a consequence of increased runoff. And taking in account this context and in order to understand some aspects of the environmental status of the San Roque Reservoir, we recently estimate a mass balance of total phosphorus by applying models to a data set obtained over 2 decades. The results show a 35% increase in total phosphorus load from 1999 to 1219. Also, this balance shows that most of the phosphorus is retained in sediments, which also increase in this period. Okay, the estimation of the total phosphorus load from the different sources, such as rivers, considering the 4 main tributaries at the northern, western, and southern areas, and also the coastal loads. We notice that the largest contribution of phosphorus in the present day comes from the coastal or perilacustrine zone, representing the 86%. Particularly, this loss comes from different sources, like fluxes through the phreatic aquifer into the reservoir, and also ephemeral creeks and diffused loads. As we confirm that total phosphorus is mainly retained at sediments, we continued studying the surface sediments in order to understand the actual sedimentary and geochemical dynamics in sediments and in the systems also. And for this, we measure some physical and chemical proxies in surface sediments in order to understand their spatial distribution, especially with regard to nutrients. For this purpose, we collect short cores here with a gravity core sampler type at different points in the reservoirs shown here, especially in the fluvial influence areas and also in the deeper zones at central and dam areas. In this figure, we can observe the distribution of total phosphorus in the surface sediments, which shows that higher concentrations are in the central and eastern areas next to the dam. And this fact is probably related to the smaller particle size found in central and eastern area. We can see it in the clay and very fine silt distribution. But also from other studies on the sediments of San Roque, it is known that iron-bound phosphate corresponds to the main phosphorus compound. This alone, our result on iron, on total iron distribution, allow us to interpret that most of the phosphorus found in the deep areas of the reservoir would be linked to the higher iron contents and to the fine grain fractions present in this area. Okay, next, to reconstruct the history of the environmental state of San Roque Reservoir, we start carrying out paleolimnological studies by collecting long sediments here at different dates using a bob core type. This collection was carried out in the central area of the reservoirs, selected to reflect the internal dynamics of the lakes, as well as the sediment and nutrient loading from the different sources. The core sediments were studied by multi-proxy analysis and dated by radioisotopes as lead 210 and cesium 137. Okay, our results from multi-proxy analysis allow us to reconstruct the environmental evolution of San Roque Reservoir. Some of the market patterns we can observe here are related to the eutrophication process. For instance, the first stage here, after reservoir foundation, was characterized by intensive deforestation and a low level due to a lower volume because the second dam was not still built. The latter is reflected in high organic proxies, such total organic carbon, total phosphorus, and also the oxygen index, that is an indicator of alloctonous organic matter. Also, we can find peaks of total phosphorus at the third stage since 1980s, and then an exponential increase of these organic proxies and also other organic proxies as total organic carbon and also hydrogen index, that is an indicator of autochthonous organic matter. Moreover, proxies related directly to primary productivity, such as fossil pigments, and in this case, chlorophyll A derivatives, shows also show an increasing trend since 1980s, and a sharp and steady rise since the second millennia at fourth stage. If we distinguish phytoplankton groups, we can, since 1918, we can see that they increase, especially those fossil pigments indicating cyanobacteria group and also chlorophyte or green algae group. And at the next stage, we can see that canthaxanthine pigment that is reflecting nitrogen fixers cyanobacteria has a very steady rise. And this probably reflects the excess of phosphorus fluxes in recent years. Okay, as a first approach to relate the multiproxy analysis with territorial dynamics, we compare the trends of the inhabitant numbers in the main cities in the basin with the fossil pigments reflecting the eutrophication process. In this case, we are presenting the chlorophyll A derivatives in black symbols and the cyanobacterial pigments in broken lines. And we can see that the fossil pigments provide evidence that the San Roque Reservoir experienced intense eutrophication since the 1980s, as shown by their increase. In addition, population growth of the littoral city, shown here, the main littoral city, Carlos Paz, and also the other cities in the basin, shows a very steady increase. For example, Carlos Paz, represented by diamonds, shows a 30-fold increase, displaying the most distinct increase during 1970s. And in addition, the population of the rest of the basin present a fourfold increase over all this period from 1940s to 1210. In order to further investigate the relationship between the eutrophication process and territorial dynamic in the San Roque Basin, we carry out an interdisciplinary study incorporating the field of geography, which enabled the examination of the intricate connection between nature and social dimensions. Some of the applied methodologies were spatio-temporal urban growth analysis based on a multi-temporal inspection of cadastral maps, historical photographs, aerial and satellite images. And it is worth to mention that the accuracy of resulting maps was verified through rigorous methods, including field observation, mapping workshops, like here, and group dynamics. This made it possible to examine the conversion of vegetative land to urban areas. Focusing on the urbanization process in the perilacustrine area, we can see from this figure that urban expansion grew markedly from the 1950s to 1990. When the main city, Carlos Paz, became a well-developed city. This phenomenon increased from the 1990s, especially in other perilacustrine localities, as evidenced by the great rise of the urban area in the second millennium. Overall, the perilacustrine area presents the most significant land use change compared to the rest of the basin. And this is a very important result because, as we have just seen, the main phosphorus load is estimated to come from this area. A deeper analysis of urbanization in the perilacustrine area reveals different processes comparing the main city, Carlos Paz, marked with red bars here, with other localities marked in blue bars. Firstly, the main city experienced its highest expansion from 1950 to 1980s. However, from the 1990s, onwards, urban area did not change, but population density, shown in red circles, increased markedly. In contrast, the remaining localities marked in blue bars show a sustained rise in the urban areas in the 1980s, as we can see here. But this growth has not been reflected by a significant increase in population density, as we can see in blue circles. It is evident that eutrophication can be mainly ascribed to the urbanization process when comparing trends of total phosphorus and fossil pigments with the urbanized areas and the population density increase. Regarding this densification process, is likely associated with the construction of high-rise buildings reaching up to 20 floors, primarily located along the San Roque's shoreline. In this figure, we can see the increase in urban density comparing the 1990s and the 2010s. The dark green areas here indicate the most densified area. And we can see that are highly increased in the 2010s. Okay, finally, we propose a model with 3 scenarios summarizing the environmental evolution of the system and the drivers regulating these changes. At the bottom, the first scenario shows an early state in a context of both fluvial influence and deforestation dominance, reflected in a high terrestrial organic matter input. Regarding autochthonous primary productivity, multiproxys analysis showed that it was comparatively lower than in the following scenarios. At the middle, the second scenario represents a state of low primary productivity and natural reforestation, and the low autochthonous contribution may be the result of a non-equilibrium state trophic condition after reservoir infilling due to the second dam building. Regarding the lower allochthonous contribution, could be associated with the reduced surface runoff related to the natural reforestation. In addition, the urban area and population density were very low. At the top, we can see the third scenario, including the acceleration of urbanization and eutrophication processes when the system reached a hyper-eutrophic condition in the last decade. This scenario is characterized by the condition of increasing nutrient load over time, as indicated by the increase of proxies related to primary productivity, for instance, fossil pigments and total organic carbon, and the increase in urbanization and population density in the perilacustrine area, coupled with the inadequacy which infrastructure can be considered to be the main driver behind the eutrophication process. Okay, but we know that other drivers are playing also in this basin. And regarding fires, as driver of eutrophication and soil erosion, this figure shows man-made fires recorded in the region in 2020, and an exceptional year for fires in the region. We note that in the perilacustrine area, the western zone was the most affected, and this is probably related because it's the only big vegetated area that is still it still remains in the perilacustrine area. We are aware that that macro charcoal, which is the proxies we are using in our studies, only records fires at a distance of approximately 6-7 kilometers. Hence, fires occurring in the San Roque Basin at a greater distance like those will probably not be detected by this proxy. And this figure shows some preliminary results of macro charcoal and multi-element profiles. Some preliminary inference on fires in the perilacustrine zone are that during the earliest stage here, they were more frequent, probably because there was a higher proportion of vegetated area. And regarding the relationship between the fires and the soil erosion process emerged when looking at the most recent macro charcoal peaks here and comparing with some elements, some peaks elements. It is possible to recognize some coincident patterns in elements indicative of sedimentary inputs. For example, the treacle inputs through titanium or high particle size through zirconium. However, we have not fully analyzed this data, so we need to go deeper to confirm these covariations and also taking into account other factors affecting sedimentary dynamics. Finally, I would like to share you some of the ongoing paleolimnological research in San Roque Reservoir conducted by our group. Some of these research lines are a comparison of water quality monitoring and paleolimnological data using phytoplankton biomass and fossil pigments, and this with the aim to enlarge the time window comparing monitoring with paleolimnological analysis. Also, we are carrying out the reconstruction of sediment dynamics through granulometric and mineralogical analysis of sediments from different areas, from tributary rivers, shore course, at different points of the reservoir along course in the central area. Also, we are going on with the reconstruction of fires in the perilacustrine zone, relating with eutrophication and soil erosion processes. And also recently we started the development of the diatom total phosphorus transfer function with the collaboration of Karina Said. Well, also I show you some future paleolimnological research that we are planning at reservoirs in Central Argentina, and these are related with paleolimnological studies with an interdisciplinary approach in other reservoirs of the region. Also, the addition of other biological addition or an integration of other biological proxies indicating different processes, for example, increases in temperature, Also, the addition of micro-charcoal proxy to enlarge the distance of reconstructed fires, and also modeling approaches to make future projections of environmental stage in future. And this we expect that will be a tool for supporting aquatic management and land use planning in basins. And the last consideration is well, what contribution we are doing with paleolimnological studies in artificial lakes on the territory. We consider that this type of research is crucial in arid and semi-arid regions, especially in a context of freshwater change, altered biogeochemical fluxes, and climate change. Therefore, this type of research helps to found a basis for assessing anthropogenic impacts on hydrosocial water cycles. They also represent an opportunity to jump the bridge between different approaches and to foster the interdisciplinary research between earth and social sciences. Finally, we consider that they will contribute to a basis for designing and implementing effective land management and planning. Well, okay, this is all. Thank you for your attention, and I invite you to ask any questions.